Okay, thank you very much, Heather, for nice introduction. And I'm very happy to be here. And of the different things I've been working on, I decided to share a small project that I worked with my former student, Shin, who is now on the faculty at University of Wisconsin. Everybody knows that Wi-Fi has become sort of a de facto standard for wireless internet connection. And as such, there are lots of Wi-Fi hotspots deployed everywhere, even small town like Ann Arbor. By the way, the Ann Arbor has 110,000 people, including 40,000 students of the University of Michigan. And from one end to the other end, if you drive, it takes about 15 minutes. It's a pretty small town. And you can see all these red dots indicating Wi-Fi hotspots. And the problem, though, this Wi-Fi is very, very useful for internet connection on the move using cell phones, all that. However, I found that whenever I keep Wi-Fi on my smartphone, by sometime in the afternoon, I run out of battery. This is Samsung Galaxy Note 3. And I found that in Korea, when you buy this Note 3, they give you extra battery. And how much this battery will be, if you want to buy, I'm pretty sure you have to pay about 40, 50 bucks. And unfortunately, this battery changes from one model to another. Galaxy Note 3 battery is different from Galaxy Note 2. So that's a very inconvenient. You have to carry one more battery in the pocket in addition to a large size of a cell phone. So why this is the case, turns out to be this Wi-Fi is one of the two main energy consumers. One would be, the other one would be GPS. If you happen to read GPS very often, it's going to eat up a lot of energy, especially if you use that as a navigator. And it turns out to be this Wi-Fi consumes typically 14 times more energy, even if it is in either listening mode, meaning that it doesn't transmit anything nor receive anything. Still, it consumes about 4 times more. Why is this the case? Well, first of all, this Wi-Fi on your smartphone spends most of the time in idle listening mode. I'll give you a little bit more specifics in a minute. Because of this Wi-Fi operates in CSMA mode. You have to wake up and listen to beacon messages. And if a beacon message says you may have something waiting for you, then you have to ask for it and wait for data to come. And then once you get all the data, you send the ACK and you go back to sleep. This takes time. And during this process, you have to operate your circuit at full frequency mode. That consumes a lot of energy. And this idle listening power consumes about the same amount of energy that you would have consumed for actual transmission and reception of data. And if you look at the Wi-Fi sort of a chip or chipsets, it consists of both analog and digital components. And the analog component is not going to be affected much by the operating frequency, but digital component is. And of course, you may ask what percentage of this Wi-Fi, the interface component contains digital compared to analog. I tried to figure this out, but it's very difficult to find. I was talking to Broadcom. They never tell me. But I was told digital would be at least about 60%, analog about 40%, although this may change depending on actual implementation. And these digital components usually stay awake and operate at full frequency in idle listening mode. I think that's the reason why lots of the energy consumption taking place in idle listening mode. So having said that, this idle listening mode will be sort of a dominant energy consumer. Okay, let's look at the state of the art in terms of saving energy. All these Wi-Fi-equipped devices are using power saving mode. Essentially, power saving mode is to schedule sleep of this Wi-Fi interface card or chip as much as possible, because during sleep mode, the actual power consumption is almost zero. So there are umpteen number of these power saving modes, and if you work on the improving power saving mode, I recommend you not to, because you're going to improve only a small percentage of energy savings, and you can't sell that to anybody. So let's look at how this works. The AP will send the beacon signals every now and then. I guess every 100 milliseconds or what, depending on implementation. And this beacon message will indicate whether you have a message or not. And how do you indicate this? This AP will indicate your physical address. I'll get to that in a minute too. And once you hear that you may have a message waiting for you at access point, you will ask for that data by sending PS pole. This PS pole will be conveyed to access point through contention mode. So this PS pole may not be delivered to access point right away, because if you have a collision, you have to wait for a random amount of time and try it again. So depending on how many other mobile clients are being served by this access point, you may have to wait longer. Somehow it is delivered to access point, then access point will send the acknowledgement. But the access point is not going to deliver the data to you immediately, because this access point must serve all mobile clients on a fair basis. In other words, if there are more mobile clients, your turn will take longer to receive this data. So there will be a certain amount of wait time or queuing delay. Finally, access point will deliver this data. And then this mobile client will send the acknowledgement back to access point. So access point can delete that data. You don't have to buffer that data anymore. Then this mobile client will go to sleep until the beginning of the beacon interval. So the power saving mode is try to maximize this. That's what you do. Before we talk a little bit more why this Wi-Fi sleeping is not good enough, we looked at the actual Wi-Fi packet traces available in the Crawdad at the Dartmouth College. And we sort of plotted the cumulative distribution of the fraction of time and also fraction of energy consumption in idle listening mode. And you don't have to read this graph. And we found less than 10% of the time, the users will actually send and receive data. And also the more than 80% of the energy spent in this idle listening mode for most people, actually more than 90% of people. I already mentioned all of this. I'm not going to talk about this. Okay, so we made two key observations and tried to come up with sort of a new solution. The first observation is idle listening mode energy consumption would be actual amount of time in idle listening mode and actual power consumption in idle listening mode. That would be total amount of energy consumed in idle listening mode. And this power saving mode is trying to minimize the amount of time in idle listening mode. That's what this power saving mode does. What about the actual power consumption in idle listening mode? Actually, I said the E-MiLi, but we have two different things. What we want to do is we want to reduce the amount of power consumed in idle listening mode. How do you do that? Well, it's based on second observation. Remember, power consumption is proportional to the speed of clock rate. So our idea is try to reduce sort of a clock frequency in idle listening mode. Well, if I do that, we'll say, oh, isn't that the dynamic frequency scaling? That's an older problem. Initially, I thought, well, we shouldn't try this because that is beaten to death. I worked on this. I think I had the 2001 SSP paper, pretty widely cited, and I quit from that topic because I can't do anything more significant. And I was talking to my former student on this. Unless we find something significant, we shouldn't pay attention to this. And furthermore, the problem is, I'm going to mention, if you reduce the clock frequency in idle listening mode, you may not be able to decode the incoming signal. So you don't know whether the access point is telling you that there is something for you. So we have a fundamental problem too. And in the end, we decide to just try this out using, it's not brand new, but some interesting ideas. In other words, our key idea is to downclock the Wi-Fi receiving circuit during idle listening mode. And therefore, we are trying to control this power consumption in idle listening mode as opposed to increasing sleep time. And graphically, what we do is that in idle listening mode, you sample incoming signal less frequently than the packet reception. Well, this is no-brainer, right? That's the easy thing to do. Why people didn't do that? Well, before doing that, first of all, if I downclock, how much of the savings of the power consumption can I achieve? We did experiments on this Wi-Fi. And if you downclock by a factor of 4, actual energy savings would be a little bit less than 50%. It's not 75% you are reducing because of analog circuits. And also we tried with the USRP. By the way, the Wi-Fi case, we use the Atos chips and all that. USRP case, even if you downclock by a factor of 8, you save about 36% because you have different implementations. But nevertheless, this is a significant sort of the power savings. If you can save by 50%, compared to achieving 5–10% savings, additional savings using smart power saving mode, this will be a big seller. Having said that, how do you solve this problem? The key challenge I already mentioned, there is a theoretical limit. Nyquist-Shannon sampling theorem says, in order to decode the signal transmitted by sender, you should sample the incoming signal twice the bandwidth the transmitter used. So if you downclock receiver circuitry, you won't be able to decode the incoming signal. So there is a good reason why people didn't look at the reduction of power consumption during either listening mode. So how do we solve this problem? Okay, so what we did, first of all, we separated detection from decoding. What do you mean detection from decoding? Well, if someone calls me, I want to be able to recognize someone is calling me. That's a detection. And then I want to understand what the other party is telling me. At that time, I'm going to fully awake and decode the information. So that's the first thing we did. So we said this is a sort of the sampling rate invariant detection, SRID. We want to have a specialized preamble in addition to regular preamble. That specialized preamble is the one having my name embedded in. So even if I am in sleep, I should be able to recognize that someone else is calling my name. If it is not my name, I'm going to continue sleeping. Since the actual transmission and the reception of the data is going to be less than 10% of my time, most of the time, my name is not being called. So I'll keep on sleeping. That's the way we achieve the power savings. That's the key idea. Okay, we came up with two different solutions. The first solution is based on self-correlation. I'll give you details. This was presented at MobiCom 2011. And another solution is a gap sense based on special sort of a pulse, energy pulses. Each energy pulse is a sequence of digital samples. I'm going to explain to you how to do that. And essentially, the gap between two energy pulses is used as a side channel indicating sort of the special coordination information to be conveyed. In other words, this gap will be my name or your name. So gap will be different for different receivers. We presented this at last year's InfoCom. All right, let's look at the first solution, E-MiLi. The idea is that we want to have a special additional preamble we call the M preamble. That is a sort of the duplicate versions of a random sequence. A random sequence is a physical address. When you associate with the new access point, during the handshake, access point will allocate a random sequence or physical address. After that, access point will communicate with you that particular physical sequence or random sequence. And you want to send multiple times this random sequence. So this means access point will call my name multiple times. Kang, Kang, Kang. Whether twice or three times, turns out to be 2-3 times is more than enough. Okay, we do that. And then the receiver side, you are going to sample this at downclocked mode. And you calculate self-correlation. If you self-correlate this incoming signal, although the each reception is not going to be a full reception of what you sent because you are operating in downclocked mode, you're you're going to detect only a subset of what was sent because of a downclocked mode. But if you do this multiple times, you will have sort of the common feature detected with a very, very high probability. Essentially, if I hear my name being called, even if I'm in sleep, I should be able to recognize my name being called with a very high probability. So that's the key idea. The basic rule for the preamble design, the self-correlation, you all know this self-correlation would be the same as the energy of the signal. And obviously, if the environment is very noisy, you won't be able to detect. The average energy of the signal divided by this floor noise should be greater than detectable signal-to-noise ratio. And you do this multiple times because you have a redundant the signals duplicate the random sequence was sent in this M preamble. And sometimes you may not be able to satisfy this basic rule, but if you send, say, C times, actual the number of sampling points satisfying this basic rule would be about the same as the length of this special preamble. Okay, this is a key idea for this E-MiLi. But there are a few the practical problems you have to address. One is what happens if one mobile client misheard someone else's name as his name, and then he's going to wake up and then waste energy, although his name was not being called, right? So somehow we have to make these random sequences very different from one mobile client to another. How do you do that? Well, we can have a physical layer address allocation. For example, say node 0 will have a separation 0, whereas node 1 will have a separation 1. Separation means there's the 0 bit. And node 3 will have separation 2, and so on. Well, if you do this, it will be much easier to differentiate different random sequences. However, though, if you do this, these special preamble size will be longer. If you have that, you will waste energy, and also you will waste bandwidth, all that. So how do you solve this problem? We have sort of address sharing. The idea is that if a particular mobile client doesn't communicate very often, it will be assigned random sequence that will be shared with many other similar mobile clients. On the other hand, if one mobile client has frequent communications, it will share this address less with others. And you can formulate these as a sort of integer programming. I'm not going to talk about that here. Another problem is when you change frequency, obviously there is overhead. Just like the dynamic voltage or frequency scaling, when you change frequency, there is a certain period unstable. Therefore, you won't be able to receive the incoming data correctly. For example, in this diagram, you are running at full frequency, and then you're downclocked, and then you have this much of a transition period, and that's typically 9.5 to 151 microseconds. And if a packet was sent during this period, you won't be able to receive. So how to deal with this problem? what we want to do is we want to downclock opportunistically. What I mean by that, for example, if you have a deterministic packet arrival, such as these request to send, clear to send, or data and act, this is a virtual carrier sensing sort of a protocol. So if you get the RTS, you know for sure CTS will be communicated. So you don't downclock in this case. On the other hand, if you have unpredictable packet arrivals, you can't tell this. How to do this? We use a simple branch prediction method in the CPU design. If you had, say, this outage event during the last window, window is defined as a sort of a certain number of these packet arrivals. If there was the outage event during the last window, then you will assume the outage will occur again, so you don't downclock. On the other hand, there was no outage event during the last window, you will downclock. It's opportunistic downclocking that way. And what's the window size? Typically, you can do with 2 or 3. That should be sufficient. This is a very engineering decision than anything else. And when you look at MAC layer protocol, this is orthogonal to existing Wi-Fi power saving mode. So this will be complementary to power saving mode, not replacing power saving mode. So if you draw state diagram, only thing you have to do is that you have to introduce one more state. Here, downclocked idle listening mode. This is a regular idle listening mode. And then the transmission and reception will be sort of between sleep and the transmission and reception mode switch will be controlled by sleep scheduling. And the sampling rate independent detection essentially manages this carrier sensing and the packet detection. As you can see, this diagram. And the opportunistic, the downclocking will determine whether to move to a regular idle listening mode or downclocked idle listening mode. Okay, you have to consider how to deploy this E-MiLi. First of all, you have to ask a question whether this can coexist with the legacy Wi-Fi, because you can't change all these Wi-Fi devices to be compliant with this E-MiLi. This is not a problem because E-MiLi nodes can detect legacy nodes very easily using energy detection. And also legacy nodes can detect these E-MiLi nodes very easily. Again, the energy detection. One problem though, the virtual carrier sensing case, we didn't consider initially, but during Mobicom presentation, I think one person, turns out to be my former student, pointed out how you deal with the virtual carrier sensing. We didn't consider initially. Later on, we found out we can handle this by using additional sort of a field ahead of a data packet, indicating this packet duration. Remember these RTS, CTS stuff, we know the duration very well because they use the PPSK and also the length we already know how long it's going to be. You can encode that. And also we found out this is useful only for handling hidden terminal problem. And perhaps you know that there was a paper in ACM SIGCOMM indicating that this virtual carrier sensing is more of an exception than normal. and therefore, by default, you turn this off. So we just finish that way, but this gap sensing case will solve this problem much easier and better. Okay, what modifications do we have to do to deploy this E-MiLi? Access point case, you gotta change the firmware in order to prepend this special preamble. And also device driver case, you have to have this random sequence or physical address allocation. What about mobile client? Mobile client case, again, the firmware must be modified to handle this sampling rate independent detection algorithm. And also the device driver must be able to receive these, the physical address sent by access point. And we have implemented these on the USRP testbed, mainly because we can't modify firmware of your smartphone, so we couldn't do that. At this point, by the way, this technology has been commercialized or licensed to world #1 smartphone manufacturer. Okay, let's look at the actual evaluation here. The first thing is how to detect the packet. In other words, how do I detect my name being called by access point? Hopefully with a very high probability with a low false positives and false negatives. And the next one is how much of energy consumption we are reducing if we detect this packet correctly. And also depending on actual the traffic pattern, you may have a different amount of savings. Let's consider the packet detection first. We consider the single link, in other words, one transmitter and one receiver. And we changed the signal to a noise ratio condition in the environment. If the environment is very noisy, nothing will work well. And we considered the native 802.11 and also the E-MiLi with the downclocking by a factor of up to 16. And we did the measurements. As you can see here, as long as the signal to noise ratio is greater than about 8 dB, that's typical the operating range. Actually, the misdetection of this packet or failing to detect my name being called by access point is very, very low. You're talking about less than 2%, which is the equivalent to the native Wi-Fi. Yes?
How many users were in this?
I'm sorry?
How many users were in this?
Oh, this is not users, just one pair of transmitter and receiver. And then also we considered the false alarm probability. In other words, somebody else's name being called by I woke up. That is equally good for single pair of transmitter and receiver case. What about multiple clients and one access point? We deployed a number of mobile devices and also one access point right here. We indicated sort of a walls blocking line of sight and also distance. Actual these misdetection and the false alarm probability affected quite a bit, especially depending on the distance between access point and mobile client. And also we considered one mobile client moving. For example, here D, I don't know where is D. D is moving. Actually, one student was moving. But in this scenario, still the the misdetection and the false alarm probability is very, very low, less than sort of 2%. What about the energy savings? In this case, we had to use the trace-driven simulation. Again, we use the crow data, and we use the large network and small network. Large network consists of more than 30 nodes. A small network consists of 7 nodes. Those are users here. Based on this low-level simulation, we found about more than 40% of savings we achieved. And also we considered the different types of traffic, again using simulation, using NS2 at that time. And here, by the way, we assumed the worst case of a switching delay, 151 microsecond as opposed to 9.5 microsecond. That's the best case. And also signal to noise ratio. The 8 dB is the most pessimistic, the operating range. And we considered 2 different types of applications. One is web browsing for 5 minutes. Another one is downloading a file of the 100 megabytes. And we saw more than 40% energy savings with the negligible delay overhead for web browsing, because that's delay sensitive. Under 20 mega, not 100 mega. Again, this FTP case, we had about the bandwidth cost 5%. We were able to achieve a 40% energy savings. What about the actual performance overhead because of the additional preamble and the switching delay? That depends on actually data rate. If you have a higher data rate, you have a more overhead. But in general, the performance penalty is not that significant. And when you consider energy savings of 40% or more, this is a very, very small sort of a cost you have to pay. Let's switch gear to the second solution. This is gap sense. This principles of gap sense is that, again, we want to use the modulation unaware preamble to each packet. This preamble essentially contains multiple energy pulses. What is energy pulse? Each energy pulse is a sequence of digital samples. And the idea, as I mentioned in the beginning, the duration of this gap between 2 successive energy pulses would be the information conveyed. For example, that random sequence of physical address will be conveyed by the gap between 2 energy pulses. Okay, I said the energy pulse is a sequence of digital samples. How do you determine the width of or length of this energy pulse? You have to have enough width so that the receiver will be able to pick up at least 1 digital sample in each energy pulse. On the other hand, it shouldn't be too long. If it is too long, your receiver will be confused that as actual data packet. For example, it should be sufficiently long in such a way that 1 energy pulse will have at least D digital samples if sender and receiver has a frequency disparity by a factor of D. So if you reduce receiver's frequency by a factor of 16, each energy pulse must have at least 16 digital samples. If you do that with very high probability, you will be able to detect at least 1 digital sample in each energy pulse. And also, because these, I'm going to talk about the gap length too. Because this gap between two successive energy pulses is short, we are going to assume the channel state won't change within that interval. All right, at the same time, you don't want to make it too long. You have to short enough and not to be confused with a regular packet. How do you know this regular packet? You look at actual header size of Wi-Fi or Zigbee or Bluetooth. And it is well understood, Bluetooth case, it is about 160 microseconds, Wi-Fi about 8 microseconds. We already know. So this energy pulse should have length less than this smallest header length, less than 8 microseconds. Okay, this gap length also you have to be careful. If it's too long, it may be misunderstood as carrier sensing duration. In other words, there isn't any signal because these two energy pulses are separated wide enough. And then these neighboring devices will say, oh, this medium is idle. I'll try to transmit. Remember, all these devices are CSMA devices, whether Wi-Fi, Zigbee, Bluetooth, they are all CSMA devices. In other words, listen before talk. So we have to make sure this idle period is not misunderstood as actual the idleness of a medium. Also, this digital sample sequence. Remember, most of these communication sequences are random in order to combat these bit errors. But in this gap sense case, you don't have to worry about that. Only thing you want to know is you want to maximize received signal strength at the receiver. So receiver will detect these energy pulse correctly. So we use the deterministic sequence as opposed to random sequence. And then this gap duration is used as a side channel to encode whatever coordination between transmitter and receiver. In this energy savings case, this duration is interpreted as this physical address. So as soon as I see the gap between two energy pulses corresponding to my own physical address, then oops, this is me, so I'm gonna wake up and run at maximum frequency. I mean the usual operating frequency. In fact, this can convey multiple different pieces of information by having multiple energy pulses concatenated together. One caution that I'd like to make is that you shouldn't use these as a regular data transport because this is not the efficient way of conveying actual information. This is used for conveying control and coordination information only. Okay. This is a lot more than energy savings, by the way. In heterogeneous network, like the Wi-Fi, ISM band case, you have Wi-Fi, Zigbee, Bluetooth. All these devices coexist in the same physical space. And in fact, because of interference between them, especially Wi-Fi is the big guy, Zigbee, Bluetooth is a little guy. And if you have a high amount of Wi-Fi traffic, Zigbee and Bluetooth may not be able to communicate successfully. This can be used for coordination between these heterogeneous devices and networks. I'm not going to talk about a lot on this, but if you look at Infocom paper, I think we have the details. All right, how do you detect these gaps? As I said, each energy pulse consists of multiple, this energy pulse, multiple digital samples here. And some of the samples are lower than this detection threshold, and therefore you won't be able to detect. But some of these sample points will be above this threshold. And with a very high probability, you will be able to detect at least one sample, one digital sample in each the energy pulse. Because the channel condition between these energy pulses is assumed not to change, which is very realistic. If you detect this digital sample here, you are going to detect the corresponding digital sample in next energy pulse as well. So therefore, this distance will be more predictable. If the inter-energy pulse distance changes from from one pair of energy pulses to another pair of energy pulses, that's going to be very difficult to interpret. We implemented this again using USRP2s. And then we compared these against the E-MiLi. I'm not going to talk about implementation and see actual sort of reduction of interference between Zigbee and Wi-Fi or Bluetooth and Wi-Fi. That's also very significant, by the way. Here, the misdetection and the false alarm sort of probability, especially these, the misdetection case, E-MiLi is better because the self-correlation will have a more sort of the accuracy in detecting these packets. But if the signal-to-noise ratio is 8 dB or higher, it is very comparable to E-MiLi. Actually, misdetection probability is around 2% again, which is quite good. On the other hand, the false alarm probability, this one gap sense outperforms E-MiLi, is quite good. In other words, these misdetection or false alarm probability is close to 0 in the common operating signal-to-noise ratio. Also, we compared these random versus deterministic sequence of digital samples in each sort of the energy pulse as a function of the disparity of a frequency between transmitter and receiver, another D value. Obviously, the larger D value, the higher probability of error in detecting these energy pulses. But compared to random sequence, digital sequence is a lot more accurate, mainly because a random sequence case, two neighboring sort of the points will smear with each other, but this deterministic sequence case, you don't have that problem. Also, what is the accuracy of detecting the gap between energy pulses? As a function of, again, the disparity of frequency of transmitter and receiver. Also as a function of the environmental noise level. As I have shown here, if environment is reasonably good, or 8 dB or higher signal-to-noise ratio, then the error probability of detecting this gap is very low. It's less than 1%, actually. That's quite good. And again, we use the same setting using Wi-Fi traces and the same setting as E-MiLi. We evaluated and then compared against the E-MiLi. E-MiLi, I already showed you that more than 40% of energy savings for more than 90% of our clients. And the CapSense will provide about the same in terms of energy savings. And also we looked at the the effects of the data rate. They are about the same as E-MiLi. What is the advantage of this CapSense? First of all, it's simpler. You don't do self-correlation, but rather this energy proceeds. This is commonly used anyway because most of these devices are CSMA devices. And also it is better compatibility than E-MiLi with the legacy hardware, since energy sensing is commonly used. And also the virtual carry sensing is very easy to implement. As I indicate to you, these CapSense can be used for coordination of heterogeneous networks and devices. And we have implemented, by the way, and demonstrated all of this, Zigbee and Wi-Fi, and also the Wi-Fi of different bandwidth. Notice that the 11AG operates with 20 megahertz bandwidth and 40 megahertz, AC 160 megahertz. And if you're not careful, this narrowband device will interfere with the higher band device, and therefore the 20 megahertz bandwidth device transmission will block 160 megahertz device, and therefore you are wasting 120 megahertz bandwidth. You can reduce these significantly, by the way. And also the coordinating the transmitter and receiver, which are operating at different frequencies, just like E-MiLi. That's what I showed you. I think my time is almost up. So the current status of CapSense, we applied for US patent. And we are in on the discussion with a couple of commercial companies for licensing. And if you Google CapSense, you can find the media hits. Actually, I don't like a media in particular, but if you want to sell this, you can't help it. Sometimes you have to do that. These are the concluding statements, and I'm going to stop here and answer whatever questions you might have. Thank you. No.
It's difficult than before, but do you have any thoughts about that?
No, GSM case, we looked at it, and actually, these slot scheduling are pretty good. The energy conservation is quite good, actually. And maybe one of the reasons why I lose energy very quickly on this is 4G LTE. But that may not be true though. If I turn off Wi-Fi, I can last a day very easily until evening. So still, Wi-Fi is a major power consumer. So whenever I travel, I just turn Wi-Fi off. But when I'm in office, I have to keep that on because inside our building, cell phone reception is pretty bad. And I shuttle from one meeting to another very often. I have to read the email messages on the move, wherever I go. So I have to keep my Wi-Fi on. So I think in late afternoon, usually my energy level of the cell phone is very low. which is very important period because my wife may call if I don't answer. There will be no dinner. So I have to keep this on. And I often forget about carrying this additional battery though. So with either E-MiLi or cap sensor, I'm pretty sure you don't need extra battery. I can last the whole day. If I extend the 40%, actually the lifetime is not 40%. If you calculate, it's about 54% the extension of a battery life. Definitely I can last the whole day.
So you are trying to save energy in idle listening. So I'm wondering if I don't want to rely on the Wi-Fi in idle listening. For example, I use some other frequency from some other band devices to wake Wi-Fi up. Say you say GSM is saving energy over Wi-Fi. For example, if I use GSM to wake up Wi-Fi, or I use some RFID or energy harvesting devices to wake up Wi-Fi, can I do even better than your approach?
So you are saying that use a GSM to wake up Wi-Fi?
Some other devices other than Wi-Fi.
I think he's saying during idle listening, you just completely switch Wi-Fi off and
Yeah,
use
so,
a
so
different
you
device.
don't have idle listening state, you just have sleep state, and use some other devices to wake up Wi-Fi.
Other device like what? GSM is not gonna do.
Some, for example, RFID, or some other energy saving.
I don't know how you do that. Right now, these cell phones don't have that capability, right?
Yes, you need to add more circuits, but to my understanding, your approach needs actual circuits too.
Okay. I don't know. We never thought about that because, first of all, I don't want to introduce a new device. Of course, you may say, is this conforming to the 802.11 standard? I say yes, but the actual implementers are not. You know, you may ask a question saying that, oh, you know, my cell phone is equipped with the E-MiLi or CapSense capability, but access point is not. Then you don't save power, right? You can't. So meaning that the access point and your mobile device must be equipped with these capabilities. And if access point is not equipped with this, I don't gain anything. Actually, I lose a little bit because I have additional, preamble, all that. This M preamble to this E-MiLi unaware access point is nothing but sort of a noise, right? Because it can't recognize. And my logic on that, by the way, when I was talking to the commercial companies, why would the access point manufacturers try to have this capability? Remember, access points are typically what, $40, $50 a piece, right? And the smartphones, depending on where you buy, if you buy in China, it's going to be $1,000, right? In US, maybe this, I think Galaxy Note 3 is about $600 if you use the Amazon.com. You're talking about the 10 times more expensive, right? And we bought this as a UCSB. All the students are carrying, say, E-MiLi equipped sort of smartphones. And you want to help the members of UCSB and your university, the IT department will say, oh, we want access point that speaks E-MiLi. So all the UCSB community members will save power, and therefore they will continue working all day long. So UCSB IT department will ask, say, Cisco or whatever, can you provide access point with this capability? Actually, I received a phone call from our university IT department, and I was told that they have 5,000 or 6,000 access points. And they want to have this kind of things to help 40,000 students and maybe, I don't know how many thousand university employees. So I don't have that influence, but you may. You can talk to Cisco saying, look, we buy this much from you. Can you have this? Or the other way is the, say, number one cell phone manufacturer. As far as I know, last year alone, they sold more than 200 million smartphones last year alone. And if they sell all of this and then make this product more attractive and sell more, what they can do is that they can persuade Cisco to have this E-MiLi speaking capability in access points. And therefore, their products will last longer in terms of energy and very happy. And more customers will buy, right? So that's another incentive. Another incentive I can think of is, say, McDonald's provides a free Wi-Fi. And their access point does not have E-MiLi capability, but neighbor store has E-MiLi capability. And all the customers are going to neighbor store, not their store. Well, the buying access point is going to cost them only $40, $50. Why not buying E-MiLi equipped access point and attract more customers? So I see a lot of incentive of how you do it. I'm not a businessman. You could do that too.
Okay, in the interest of time, let's thank Kang again. And
Thank you.